So now let's talk about banked and unbanked curves. Motion on a flat curve. As the car travels around the curve, the net force on the car is the centripetal force. This centripetal force is always directed towards the center of the circle that the curve is a part of. So now the next question is, as you go around in a circle, what is that force that's providing the centripetal force? When we were talking about masses attached to a string, we said it was the tension, right, that was providing the force that was keeping things going in a circle. Now, what is the force that's providing the centripetal force in this case? And the answer is, it is the frictional force between the road and the tires that is providing that centripetal force. So in this case, if the tires are worn out in the car or if the road is icy, this frictional force will not be available. So the car will not be able to move in a circle and it will keep going in a straight line and therefore go off the road. So let's talk about the motion on a flat curve. What are the different accelerations on this car as it rounds a curve? Well, there is going to be acceleration along the y-axis and an acceleration along the x-axis. So along the y-axis, is the car going up and down? If the car is not going up and down, then that means the acceleration in the y direction is 0. And the acceleration on the x direction, however, is the center-seeking acceleration, the centripetal acceleration of the car, which is given by v squared over r. So if you were to draw a free body diagram of this, the forces on the car are going to be frictional force that acts inwards, the acceleration that acts inwards, the normal force that acts upwards, and the force of gravity, which is the weight of the car pulling it downwards. Now, in terms of frictional forces, the sum of the forces is the only force that's acting on it is the frictional force. So centripetal force is equals to the static friction. And if you do this calculation real quick, F is equals to mv squared over r, and frictional force is equals to mu naught n, and n equals mg. So the quick calculation will show the maximum speed in order to round this curve properly is going to be given by v squared over r equals mu g. So now let's talk about this. Radius of a circular path. So let's say if there was a car that was going around this curve. What do you think is going to happen to the car as it goes over the radiuses, the different radiuses? Well, we know F equals ma, which is equal to mv squared over r. So smaller radius will mean that there is a larger force that's required to keep it going in a circular motion. And this is obvious also from this expression because F is inversely proportional to 1 over r. That means larger radius requires less force and smaller radius requires more force. Engineers have now learned how to bank curves in order for the cars to safely travel around the curve without relying only on friction to supply all the required centripetal acceleration. So here's my question for you. So pause this video here and go see if you can figure out, knowing what we've already know about how many forces are acting on the cars, assuming no friction, and then assuming friction is present. So try it for yourself. Pause the video here. Go and try to write down the force equation in both of these cases. Another thing that you should be aware of are the basic definitions of what we are talking about when we talk about banking curves. Banking angle is the angle by which you are going to raise your tracks or your road in order for the car to travel safely. Where r is the distance from the center of the curve, and it's also called the radius of curvature. So motion on a banked curve. The effect of banking is to tilt the normal force towards the center of curvature of the road, so the inward radial component, Fn sine of theta, which is given by this expression here, can supply the required centripetal force. So vehicles can make sharp turns more safely if the road is banked. If the vehicle maintains the speed for which the curve is designed, no frictional force, additional frictional force, should be needed to keep the vehicle on the road. So what is the ideal banking? Banking the curve can help cars from skidding. We know that. In fact, for every banked curve, there is one speed where the entire centripetal force is supplied by the horizontal component of the normal force and no friction is required. This happens when Fn equals mv squared over r, completely. So now let's look at a problem. A highway has a curve that has a radius of 825 meters. At what angle should the road be banked so the car traveling at 26.8 meters per second has no tendency to skid sideways on the road? Now, here's a very important thing to recognize. No tendency to skid means the frictional force is 0. So now, what are we supposed to do when we have a question like this? As always, we are going to start by writing out all the information that's given. 825 meters is my radius of curvature. My car is traveling at 26.8 meters per second, and I need theta is what I need. Okay? So I'm going to draw a picture, because that's what I always start with, where theta is this angle, and here's my car that's moving forward. And in that car, I will always have a normal force acting on it, and I will have an mg that acts downwards on it. Okay? And I know the centripetal force is always going to be directed towards the center of the circle. So in order to solve this problem, I am going to rewrite my sigma fx and sigma fy. Now the question is my choice of coordinates. Here's where it becomes tricky. You could use coordinates any way you want. You could use a coordinate system that looks like this, or you could use a coordinate system that looks like this. It is your choice. However, in this case, you will now have to remember to resolve your forces, both fx and fy, the centripetal forces, into 2. If you choose this system, then the only force you need to resolve is the normal force into these components x and y. So again, it's your choice. You choose what you want to do. I'm going to choose to do it this way. But feel free to do it the other way as well, just as a matter of principle to see if you can actually do it. Okay? So these are the two equations we now have. Now this is the angle theta, right? So I need to be able to resolve my normal force in terms of x and y. Oops. So my normal force can be resolved in terms of my coordinates. This will give me my n, y, and this will give me my nx according to my choice. Okay? And this gives me the angle theta. Okay? Okay. Now, all the components are there, all my forces are here. So for fx, I have nx. Here, that force, it is directed towards the plus side. Okay? Now for Fy, I have an Ny, which is directed towards the positive, and I have an Mg, which is directed downwards. And on this side, I have no forces acting on my y direction, but I have a force mv squared over r, which is a centripetal force acting inwards. Okay? So equation 1 and equation 2 can now be reduced down to mv squared over r equals nx, and equation 2 can be reduced down to 0. I'm not going to write 0. mg equals ny. Now, nx, if you look very carefully, is actually equals to your normal force times sine of theta. And ny is actually equal to your normal force cosine of theta. So I'm just going to plug those values in here. So nx becomes n sine theta, ny becomes n cosine theta. So my equation 1 reduces down to mv squared over r equals n sine theta. And this one reduces down to mg equals n cosine theta. Okay, now we're going to use the same trick by dividing the two equations. So I'm just going to divide these two equations. N's go away, m's go away, and my answer comes out to be v squared over rg equals sine theta over cosine theta. Sine theta over cosine theta, use the trig identity, it is equals to tangent of theta. And so this implies that v, ooh, this looks like an r. This is not an r. This is v, right? So v squared over rg equals tangent of theta. That gives me my banking angle. So now that I have this expression, I can come back to here, and I have a v, and I have an r, and I know the value of g. I can calculate theta real quickly. So theta will be tangent inverse of v squared, which is 26.8 squared, divided by r, which is 825 meters, divided by 9.8. You do the math real quick, and your banking angle comes out to be 5.1 degrees. Okay? So this is how much the road needs to be banked in order for a car traveling by this speed to round the curve properly. Now, for homework, what I would suggest is for you to try to see how much the banking angle will change if, let's say, I was given the same exact problem, but with a small force of friction, right? So if, let's say, this question was changed in order for me to have a mu of, say, 0.5 between the tires and the road. How will this question change? I'll give you a hint. What you need to do now is to reorder all of your forces and stuff in order to include the frictional force. So which direction should the frictional force be? If left to its own devices, where will the car want to go? It wants to go outwards, right? So what is keeping the car from moving inwards is the centripetal force. So the force of friction is going to be directed inwards, right? So here's where your force of friction is going to be. You need to be able to resolve them in terms of components, just like x and y. Plug those in here, solve these expressions, and everything else will remain exactly the same, and you can come up with your banking angle.